Alright, 6.5. Welcome to word problems here. So, as I just stated here, 6.4 we learned how to solve equations here. Now we're going to use that information to solve word problems here. Start off pretty easy. We're going to work with maybe something called number problems, as the book sometimes calls them. Then we're going to move on to more like physics problems sort of set. Or they call it motion problems, that's what they call them. And then something called work problems. And then we'll finish off with graphing. So in your mind, sort of have that in your mind here. So number problems or algebra problems, motion problems, work problems, and then graphing. That's how it's sort of broken down. Okay, anyways, very similar to the word problems we have been doing. Hopefully you're becoming a little bit more familiar with word problems. Maybe the online stuff has helped a little bit with word problems. Okay, maybe not. Okay. So one number is twice another. There it is. The sum of their reciprocals is 9/2. So again, what we do is we make x equal something. What are we trying to find? X would be the smaller number. You can say the first number, whatever you like. My preference would probably say the first number, or one number, another number, something like that. Okay, it says one number is twice another. That means 2x has to be the second number, or the larger number in this case, however you want to label it. Labeling is not that important. But it says the sum of their reciprocals. So we take the reciprocal of x, which is 1 over x, reciprocal of 2x, which is 1 over 2x, and we add them up to give you 9/2. Alright, and we learn now we do 6.4. At this point we ask ourselves, even though it doesn't say it anywhere here, what can x not be, or else we're in trouble. This caused us some problems last time here. What can x not be? It cannot be 0. Because if I put a 0 in here, it'd be 1 over 0, and that does not make sense in math. Plug in a 0 in here, 2 times 0 is 0, and that's in trouble because then it's gibberish. So off to the side somewhere, I like to do this first because it sort of keeps it in your mind saying, oh, I got to check something at the end. Okay, with that, then we start multiplying through by the common denominator, which in this case is just 2x. So 2x multiplies, technically should multiply both right and left-hand sides, but we multiply every single term because every single term usually has something to cancel. Once you get to this step, it is so easy. Simplify each of the sides, solve for x, and then you're good. And then what we're going to do is just check one little extra step here. Can I accept 1/3 as my answer? Absolutely. Can't accept 0, but I can sure accept 1/3. Okay, we do this little step right here, x cannot equal 0, only if there are variables in our denominator. If we have x's or y's or z's, that's the only time we really need to check, because that's the only time you can actually somehow get a 0 there. Like for instance for 9/2. That's a fraction. I can accept anything I like for this number, right? Because 9/2 is 9/2. Kind of like this, maybe like x over 2. There is no number for x. If I plug it in, will cause me problems. If I plug in a 1, it's 1/2. Plug in a -1, it's -1/2. If I plug in a 0, that's still okay, because 0 divided by 2 is 0, right? The problem comes in is right here, when I'm left with a situation that looks like this. Now there's some problems, right? I can't have a 0. I can have a 1, I can have a -1, I can have 5, I can have 28, but I can't have a 0 because now I'm saying that 0 is going to divide into 2 a certain amount of times, and that's not the case. Okay, good there? Just a little quick refresher here, and so let's jump to our problem here. So one number is 3 times another. Okay, fine. I think we can handle that here based upon example 1. Hey, give you guys a little bit of time. Try it yourself first here. See if you can solve it based upon example 1. Alright, I'm going to start here. So again, label. So one number, that's the way I did it. Again, first number for you, whatever you like. The labeling itself is not that important. But the other number is 3 times another. So how about 3x would be, you can say the other number, you can say another number, the second number. Again, whatever the labeling that you want to put in here. But it says the sum of their reciprocals. So here we go, 1 over x plus 1 over 3x is equal to 4 over 9. In this case, we've got to think about this here. Let's see. What can x not be? Again, that little 0 problem took care of. Next, what's my common denominator?
9.
Cool. Okay, good. I heard some people say 3, some people say 9. So here we go. This is the way I do it, okay? I look at my coefficients, or my numbers themselves. I see a 3 and I see a 9. What's my common denominator between 3 and 9?
3.
9, right? It's always going to be the bigger number. It's going to be the number 3 goes into and number that 9 goes into. So it's always going to be a bigger number.
I always thought it was the lowest common.
Okay, let's talk about it. Because, again, just to clear up people's minds here. What they mean by lowest common denominator, the question came up is, what do you mean by lowest common denominator? So, what's the common denominator between these guys?
6.
6. Would 12 also work?
Yeah.
Would 18 also work? How about 24? See how we can go on and on with this common denominator. We can go on forever. But the least common denominator is the smallest number that both of these numbers will go into evenly. That's what they mean by the least. Because many students...
We're doing fractions.
Many students...
It's a little bit different. When you're... There's another section that deals with that, and you have to do the higher one. Because the higher one will be 1. And then... Okay.
Good?
I'm with you now.
Okay, sounds good? No?
Sorry.
Don't want to lose anybody here, so we're...
Something where you pick the biggest number and then the smallest exponent or variable.
Oh, yeah.
Something like that. She has
Yeah,
the answer.
yeah. Factoring works the exact opposite way, right? You see a 3x and a 9, you're going to take out only a 3. Common denominators, exact opposite way, yeah. So, let's talk about it. Because it's too cool not to talk about it. So, whenever we talk about factoring 3x plus 9, we always talk about this. We always talk about the greatest common factor, right? Remember that? Again, so it's...
Confused.
Yeah, it's the biggest number that will go into 3x and 9. In this case, it's going to be... Are we okay with 3? Right? Kim, real quick here. Why did they say why is it the greatest common factor here? And I'll show you here real quick here. This guy here. Yeah. 2 will go into those, right? 4 also will go into those. But we want... That's how we want. We want the greatest common factor. That's a multiplier into those numbers. Cool. With okay, good there. That was good enough of a background on it. Again, don't mind going into things like that because I want to clarify things in your mind here. I'd rather do that than lecture and then everybody's confused. Okay, so let's go for it. Common denominator, everybody said, was
9.
9. And then I look at my variables. For common denominator, we always choose the greatest exponent. So I see x to the 1, I see x to the 1, therefore it's just going to be x to the 1. Cool. Each of these get multiplied by 9x. Now let's start canceling, because after this step, that's easy. Just need to get through this step. Right?
Never mind.
Okay, x's are gone here. We still have a 9. 9 times 1 is 9. Over here, ooh, that's kind of fun. Look at that. The 3's and the 9's are going to disappear as well. So 3x, 9x, and how about an extra 3 left over on top? All right, 3 times 1 is a 3. Going over here now. 9's are gone, right? 9 is gone, 9 is gone, so therefore x times 4 is 4x. All right, 9 plus 3 is 12. Divided by 4, and we got ourselves, voila, x equals 3. Can I accept that as the answer?
Yes.
Yes.
Okay. Only thing we haven't talked about. This is a word problem. I didn't see no x's up here. Anybody see any x's up here?
No.
No. So I can't just say x equals 3. Doesn't make sense. So in an English sentence, can you write for me the answer to, or the answer to this, or finish out the statement here. Find the two numbers. Ah, cool, yeah, there you go. The numbers are, or the two numbers are 3 and 9, right? Because the 3 and the 9 being 3 times bigger. So again, for each of these here, like we did with the previous word problems here, just a sentence in English. Make sense of the numbers, make sense of the units if there are any, and make sense of the variable. What the variable represents, what the number is, and what the units are, if there are any units. Okay, so that's where the number problems were. Let's jump to motion problems here. Some physics problems here. So a boat travels 26 miles up a river in the same amount of time it takes to travel 34 miles down the river. If the current is 2 miles an hour, what's the speed of the boat in still water? So we're trying to figure out how fast is this boat really going. We throttled it at full speed all the way up the river. We throttled it at full speed down the river. And let's see, how fast is this thing going? Did we have a discussion of why this does not happen as we drive cars? Or no? Okay, we'll get there. Okay, how's the problem done? And for word problems here, this particular one, we've got to think of this little formula. So distance is equal to rate times time. And we looked at that earlier before, right? This time though, notice what's happening here is that we really don't know time values. We know it's the same amount of time, but we don't know what that time value is. So our problem is that time is our sort of our variable. That's the stuff we don't know. So let's make this formula in terms of t. How should we do that? How should we solve for t here? Divide by nope.
By R.
There you go. Yep. Let's divide by r, because then we solved for t. D over r is equal to t. Okay, that's one thing we have to keep in our mind. Okay. So whenever think about time being what we don't know, we're always just going to take your distance and we're going to divide it by your rate, how fast you're going. Okay, now we're ready to start. I say that x is the speed of the boat in still water. And usually you can get that from the question itself. Now let's talk about a boat going up the stream and the current of 2 miles an hour. So as the boat is going 2 miles an hour up the stream, the problem is the current, because the current is going backwards, it's actually subtracting 2 miles each minute here that it goes, or each hour. So since it's going upstream, we say x minus 2 is going to be really the speed of the boat going upstream. So you guys tell me here, what would be the expression for the speed of the boat going downstream?
Plus 2?
Yep, that's how fast the boat was going. And then we are now adding the current this time, because now the current is actually pushing us along.
To go down?
To go down, absolutely. Okay, so this happens in boats. This also happens in airplanes, because there's a wind up there. And so me being the math geek, of course. Did I tell you the story about my wife going to Washington or no?
No.
I didn't? Okay, see, I'm confusing the two classes here. My wife and I went to Washington a few years back, Seattle-Tacoma Airport, and we left Fresno. So, of course, I have to do something math geeky. And so as the airplane is just about to take off from Fresno, Yosemite International, I click on my stopwatch, and I go click. And it flies, yeah, blah, blah, blah. And as soon as it lands at the Seattle-Tacoma Airport, I go click on my stopwatch, and it says 1 hour and 55 minutes. So that's cool. So a week later, we're flying back home, and we're leaving the Seattle-Tacoma Airport, flying back to Fresno. As soon as we take off, I click on my stopwatch. We land in Fresno, I click it off, and it says 2 hours and 10 minutes. It's kind of weird. So Why the difference? There's a difference of 15 minutes.
The wind.
The wind, of course, yes. Okay, when is the wind going against us when we're flying? Flying there or flying back?
Flying. Doesn't it depend? Like,
Depends on the time, that's all it depends. It was 1 hour and 55 minutes to Seattle, and it was 2 hours and 10 minutes back. Yeah, on the way back, the wind was against us, right? When we were flying there, the wind is actually carrying us along a little bit here. We had less wind resistance. Okay, we good? Now the question always comes up, Mr. H, how does that not happen on cars? Why do I go from Fresno to Coalinga, Coalinga to Fresno, and it's literally if I drive 70 miles an hour, I'll get there right at the same time? Anybody with an answer?
because you're like on the ground.
On the ground, there's more friction on the ground. Okay, so the wind is not that big of a factor. Okay, yeah, because there's more friction with the ground. But let's say we had a humongous wind, and then you still were driving. What would you do normally? Not a humongous wind, but let's just say there was a big wind going against us. Wouldn't, there you go. We just press the pedal a little bit more, don't we? Because we see the little speedometer that says 70, like, okay, cool. Well, I say 70. Okay, we good there? So on cars it doesn't matter because we just press the gas pedal a little more, if anything. And plus the friction with the ground is different. So, but yeah, with rivers, with ocean currents can become even more crazy because as you're going straight, you could have an ocean current that's sort of on your left-hand side and pushing you left. So then what the person that's steering the boat, what he has to do, he has to compensate by pushing a little bit right. So you technically are going right, but you're really going straight, and it's kind of fun. Now you're into trigonometry at that point. Now you're talking about angles, you're talking about things like that. So it's kind of fun there. Okay, let's go for it here. So once we have this set up, this is cool. I read this in a math textbook. Well, it was like a word problem. It was like a whole book about word problems. And they had this little grid, and he said if you can make this little grid, all these problems you can solve. All mixture problems you can solve. There's like a whole host of problems you can solve just by making this little grid. That's kind of cool. Okay, D equal to R times T. And then the situation is one way we're going upstream, the other way we're going downstream. All right, let's fill in whatever we know. First of all, 26 miles, is that right? That's how we traveled? And we traveled 34 miles down the stream. So that's downstream. Okay, we're good there. Let's see, what's the rate? How fast was I going upstream? I haven't got there yet. What's my rate since I'm going upstream?
2 miles. X minus 2.
Cool. It was x minus 2, right? Because I'm going upstream and then the current is pushing me back at 2 miles an hour. So it's this one right here. So speed or rate, it kind of means the same thing here. All right, downstream, x plus 2. Everybody good there? So notice this last column called T. T is not filled in. Because the last time we were doing these problems, the D part was not filled in. What we did is we multiplied through to give us that D part. This time, we have this little formula, D divided by R. That's what T equals. So we're going to go over here. We're going to say, okay, T is D, that's this guy, divided by R. Same thing over here. You guys fill in the last column, or fill in the last cube there. All right, hopefully we got this right here. Okay, word problems, distance problems, you're going to have it one of two ways. It either will say the same amount of time, or it'll say total time. Okay, same amount of time, what we do here is we just put these two equal to each other, because that's what it means, same amount of time. It took this much It took the same amount. The other kind of problem that you might see is it says the total trip took 5 hours. At that point, you're going to add these two together to give you 5. Good there? That's the only two ways you can get distance problems. It's either grand total for the trip, or they compare these two to each other in a certain amount of time. Okay, I think we know how to do here. All yours to finish off this. Let me rewrite it on the next slide here real quick. All right. Let's see, what should I do? The only thing I should say is this real quick before we begin. Give me those. Give me my restriction for x. Perfect. Positive 2, negative 2. All right, this one, if you remember from the previous class, something called cross multiply. This one would be the easy one to cross multiply. Cool. I'm going to do it the old way though. I'm going to do it by multiplying by a common denominator and just seeing what's going to happen here. Notice the x minus 2's are going to cancel on the left hand side. So it's almost like same thing as cross multiply, right? You're going to multiply the top and bottom diagonally here. 26 times x plus 2. On the other side, x plus 2's cancel, so therefore it's 34 times x minus 2. And hopefully you guys are almost done. Yeah, that would make 68.
So these aren't the ones where you multiply them separately?
All right, I would probably subtract 34x from both sides. I'm going to get a negative 8x. How about subtract 52 from both sides? Negative 120 divided by negative 8. Anybody with an answer? Of course I'm not going to give you the answer. I'd go with 15. Yep, 20 divided by 8. You've got to divide those by 4 initially, and then you get, 2 goes in 15 times. That's cool. All right, English. Sentence in English that makes sense of what the variable means, the number itself, and the units given.
The speed of the boat in the water is 15.
Perfect. Yep. Yeah, I would agree with that. Here, the speed of the boat, and the only thing I would include is in still water, because that was the question initially, right? What's the speed of the boat in still water? It means if there is no current at all, what's really happening with the boat here? So the still water is 15, and then the units come in as 15 miles per hour. All right, good there. The whole setup, formula that we need, setting up in those boxes here, thinking about what we know, what we don't know, and setting up the equation and solving. Okay, next one is going to be a word problem, very similar. How about this here? Let you guys get a head start on it first, and then we'll see if we can do it together here. So Tina is training for a biathlon, which means she's going to do 2 different activities here. She rides her bike 15 miles up a hill and then 15 miles back the same hill. The complete trip takes her 2 hours. If her downhill speed is 8 miles per hour faster than her uphill speed, how fast does she ride uphill? All right, remember the little formula right here before we get started. Oh, what is x, first of all?
The speed.
I'll go with speed. Anything else?
Speed. Going up the hill?
I'd go with that, right? Let's see. Her downhill speed is 8 miles per hour faster than her uphill speed. Why did it turn all weird? Pulp is breaking. So the downhill speed is being compared to the uphill speed, right? If that's x, what would be the downhill speed?
X minus X plus 2?
Eh? It's me here.
X plus 8.
X plus 8 would be good. X plus 8. And think about why x plus 8. Read the sentence, see if you find it. Yeah, her downhill speed is 8 miles per hour faster than her uphill speed. So uphill speed is x. That means x plus 8 would give you speed of bike downhill.
Is it the same formula as the last one?
Uh-huh, there's my little grid. Hey, D equal to R times T, awesome. In this case, instead of upstream, that would go uphill, we'll go downhill. And then the only little formula extra is we don't know T, so think about what the formula is for T. Okay, let you guys try it yourself here first. All right, let's go for it here. So, distance, everybody okay with 15 miles? 15 miles there. Uphill, we already have it. Everything's set for it. Is x. Downhill then, x plus 8. And then remember T is, again remind you here, it's D over R, right? So how about 15 over x, and how about 15 over x plus 8? Okay, the complete trip took her 2 hours. So we're not going to equal them to each other. Remember, that was the last one. That was in the same amount of time. That's when we make them equal to each other. This one's going to be adding them together and giving you 2. Good there? All right, I'm running out of space here. Let me rewrite it on the next slide here. Okay, so first of all, restriction is, which I forgot to finish the restriction off last time. We'll talk about this one. What can x not be?
Can it be 2 things? Oh no, wait, 8, negative 8.
It could be 2 things, yeah.
But X is 0, so.
Yeah, x can be equal to 0, and x can be equal to negative 8. Yeah, for every single fraction, if there's a variable there, it needs to be thought through. Okay, common denominator is x and another x plus 8, right? We need each of those, right? We need the x, we need the x plus 8, x times x plus 8, and x times x plus 8. All right, x's are gone, so it's 15 times x plus 8. Now I'll let you guys finish off the other part. All right, next we go with the x plus 8 cancels, so how about 15 times x? On this side, nothing cancels, because there's no fraction to cancel with. So how about 2x times x plus 8? We're gonna multiply the rest of it out on the next step. All right, distributing the 15, multiplying the 15 and the x, and then distributing the 2x. So 2x times x is 2x squared. 2x times 8 is 16x. All right, and as soon as I see this here, notice I have an x squared term. I also have x terms, so all of a sudden in my head I see a factoring, factoring, factoring. All right, before we do that, let's just combine anything we can on each of the sides here. How about the 15x here and the 15x here? Would that make 30x? I'm just going to simplify as much as I can. There it is. 30x is simplified down. And now for sure I'm going to have to do factoring because that x squared is still there. The x terms are still here. So let's see, let's move everything over to the right hand side. So let's subtract off the 30x, subtract off the 120, 0 equals 2x squared, and minus 14x, and minus 120. Alright, your job to finish it off from there. Okay, let me rewrite this here because I don't have time, space on the other one. So hopefully you did factor out the 2. Left you with this trinomial left. And then at this point, let's see, I need two numbers, multiply to negative 60, add to a negative 7.
12 and 5.
12 and 5 is perfect. Okay. So then we got x and x, and we have a negative, let's see, how about a positive 5 and a negative 12? Would that do it? Okay, we did this when we were doing factoring, right? You can either just erase the 2 out of here, just cross it off, whatever you want to do. You can officially take it out using math stuff by saying, okay, 2 is equal to 0, or the x plus 5 equals 0, or the x minus 12 equals 0. And then as we go back to the 2 is equals 0, what you do is you put a slash through here, right? You're saying that's not possible. So again, what your book does, it just, the 2 sort of disappears into Never Never Land, and they just sort of never talk about it.
Are there like any shortcuts for these?
All right, x is equal to negative 5, and x is equal to 12. Okay, as we look at this here, that doesn't make sense. Does x equals negative 5 make sense? Everybody says yes. All right, we'll see. Let's go back to the word problem. What does x mean? X is the speed of the bike uphill. Does it make sense that the bike is going at negative 5 miles an hour?
No.
No. So as we jump to this here, we're going to say that is not making
What if
sense.
you're, like, pedaling backwards?
You're still pedaling. You're still going a distance. So for these word problems, as you come to the end, you got to think about what numbers won't make sense. Now let's go back over here real quick here as well. Let's jump to this one. Would 0 make sense?
Yes.
No, because that means we didn't go anywhere then, right? So then there's no word problem to even talk about, right? Would negative 8 make sense? Yeah, negative 8 actually won't even make sense because of the whole concept of its distance, right? Does that make sense? So those would have been out already. Do we need to check them? Yeah, we do need to check them just to make sure. But if this is a word problem, and I'll just say it this way here, how about that? If this is a word problem that makes sense logically here, then the number itself at the end is going to make logical sense. Right? The restriction is not going to play a part in it. So if it makes sense that a person can go up a hill, go down a hill faster, and then take a certain amount of positive hours to do it, the number itself is going to work out at the end. And so in this case, there it is. X equals 12 is the only one that really works. All right, English sentence, go for it. Can you make sense of that 12? What does it mean as far as a variable is concerned, the number itself, and the units?
She rides uphill 12 miles per hour.
Mm-hmm. So she rides uphill at 12 miles an hour. Perfect. I just put in her uphill speed was 12 miles per hour. That's fine too. Depending on the scenario, depending on what you're talking about, this could be past tense or present, right? Depending if it's something still happening or she.
It's her. We should have her name.
Tina, yes, absolutely.
You can be the math geek. I'll be the English geek.
Okay,
Okay.
fair enough.
I'd rather be a math geek though.
Okay, so those are the distance problems. Again, two different types. You set the time equal to each other, or you add the time to a certain value. All right, now these are something called the work problems. Oh boy. That means there's a certain kind of work that needs to be done. Usually it's some kind of rate that's like this, filling up a faucet, maybe filling up some kind of canister, something where there's something being filled. As you guys are putting it together or writing it down. My father told me to, when I was in college, my father told me to put the two hoses that we had and fill up our pool because we had it replastered, right? And so somewhere in the manual to our house, it actually told us how many square feet or how much volume there is in the pool. It actually gave us the number when they were building the pool. I guess we still have the original papers when they built the pool. And so what I did is I took the hose, because that's the way we were filling it, and I ran the hose for 15 minutes. And I figured out how much water 15 minutes would put in. And then after that, we had a big tank next to the pool, so I'm like, oh, cool. So then, of course, then I dumped the water. Then I started, and I did this calculation, practically almost the same calculation, which is how long is it going to fill the pool? And so then I timed it so that when I come home, I want to see the pool filled up. And it was kind of cool. It actually worked out. I was like, yeah, I am the math geek. That's right. So that was a fun little experience. Okay, so let's go for it. A tub can be filled with cold water by the cold water faucet in 8 minutes, while the drain empties the tub in 12 minutes. How long will it take the tub to fill if both the faucet and the drain are open? And of course, sometimes word problems don't make sense, because what you would do is you just close the drain if you want to fill something up, right? But in this case here, let's go for it here. So, work. This little W stands for work, but notice it's the same thing that we talked about distance. Look at that. Distance is equal to rate times time. Work, W is equal to rate times time. Same exact formula, just means a different symbol here. Right, if you're going like 50 miles an hour and you do that for 2 hours, you should be 100 miles away, right? From your distance. So that's the distance part. If you can type at 20 words per minute and you're typing for 3 minutes, you should be about at 60 words, right? All right, sort of that's the work aspect of it. So it's the same formula, just means two different things. Cool. All right. So you guys tell me, what in the world is X?
X is the tub.
Let's see. I read you the question here. How long will it take to fill the tub if both the faucet and the drain are open? So here you go. Amount of time to fill the tub with the faucet and the drain open.
Is it fair to say that X is what you're trying to find?
Yeah, most of the time. The question is, isn't X always what you're trying to find? Almost always. Sometimes what you're trying to find, let's say it's a triangle problem, and you say find the two legs, right? Then you're trying to find the X, then you're trying to find the relationship to the other one. Just like we did with the numbers for our first problem, right? First problem that we did. Find the two numbers, and we said the two numbers are 3 and 9. So not necessarily the X is it.
That was a number problem, the first one?
Uh-huh.
And the other ones were time problems?
They call them motion problems. The book calls it motion. So number problems, motion problems. Now we're on the work problems. Okay, look at this little thing right here again. Look at that. Hey, a little grid. Love it. So on top, W is equal to, I think you guys can guess what's on top.
W equals R times
T is good. Okay. So what are my row headers? What's doing the work?
The drain and the faucet.
Perfect. Yep. Faucet is doing one kind of work. The drain is doing another kind of work. Okay, these are going to be a little different than what we did with the distance problems. They work a little different here, so let's talk about it. But they always work the same way. All work problems are going to work the same way. All right, so first things first, the rate. This is the fun part about it here. So faucet. Faucet can fill that whole tub in 8 minutes. So the rate that the faucet is working at is 1/8. So if we're talking about minutes, you always kind of go back to the, okay, if it can fill it in 8 minutes, how much of the work can it do in a single minute? In a single minute, it can do 1/8 of the job. Good there? Okay, then let's do this one here. The drain can empty it in 12 minutes. So what kind of a job can it do in a single minute? Hey, 1/12. We're all good there. Okay. For T, for time, the time is, hey, isn't X is really what our time is? Amount of time. So guess what? We just put in, there it is. Put X's for our time variables. Now the only time these would be different is if it said the faucet started going and 2 hours later the drain accidentally opened. See that?
Would
Then
it say that?
say again?
Would it say that? Like
Not in Math 63. It never happens. The drain never opens in Math 63.
Math 61.
I'm sorry, in Math 61. In Math 61 it does not happen. In Math 63 occasionally it does happen. Or the drain opens up later. Alright, what do we do here? Notice there's only one space left. We used to divide to get us this one, right? But what's the relationship between R, T, and W? It's a multiplication relationship, right? So what's X times 1/8? Yeah, you can write 1x8, or you could write X over 8. This one would be X over 12. Alright, so how do we put this here? Let's see, how much time will it take to fill if things are both working here? So this is what I got, X over 8. That's one piece. And kind of careful here, because the drain is undoing the work of the faucet, we're going to put a minus sign. We're going to put X over 12, and then at the end we're going to say 1. So what in the world does that 1 mean? It means that we have one sink. Oh, sorry, one tub to fill. Sink, tub, almost the same thing.
How come we put x8 minus x12 and not x12?
Ah, cool. Yeah, because the faucet is doing
The work.
putting in the water, and the drain is taking out the water. All right, in my my little filling up the swimming pool experience, I had 2 hoses happening at the same time. So this little minus sign would have to turn into a plus, right? It would be the work of the one hose plus the work of the other hose. We good? So I have to understand the relationship. In this case, it's a minus because the drain is undoing the work of the faucet. If you had sort of like 2 faucets, both open, then it would be 1/8 plus 1/12 because they're both helping each other at that point. Okay. The 1 stands for, the 1 stands for because this is just one tub. This is one work. If it had to fill 4 tubs, then this would be a 4. That's right. So it's one single tub to work on. Hey, any restrictions here?
No.
No, because there's no variables on the bottom. Cool. What's my common denominator? 24. Let's multiply by 24 and let's finish it off. Alright, let's go for it here. Multiplying through by 24. 8 goes to 24 3 times. How about 3x? 12 and 24 twice. How about a 2x? And then how about a 24? Hey, this was kind of fun here. Again, the math is not that complicated. It's the word problem, setting it up, putting it all together. That's probably, don't want to get you lost in the math here. It's more of just, can we set it up? Okay, x equals 24, and hopefully you wrote the sentence in English already. So it will take 24 minutes to fill the tub. You can say it like that. You can keep on going and say when the faucet is open and the drain is open. But in this case, this suffices here. It tells us what the variable is, tells us the number, and tells us the unit value. think most people had that already, so that's cool. Okay. So those are the word problems here. One little extra piece in section 6.5 is this whole concept of graphing. And it says, for example 5, it says graph the solution y is equal to 1 over x. Since we'll be dealing with rational equations or rational expressions, the question is how do you graph a rational expression? So a rational expression, it has two weird things in it here. First of all, it has this piece right here where the graph sort of cuts off. Hey, and look at that. What's our restriction on there? Yeah, our restriction is 0, and that's when we have a break in the graph. Cool there? And then from the rest of the time, yeah, you can put in points here. So -3 plugged in. And remember, this is just a reciprocal, right? So as -3 goes into here, you get yourself a -1/3. As -2 goes into there, you get yourself a -1/2. So and so on and so forth. Notice if these are big integers, these are fractions. If these become fractions, then these become integers. So there's a sort of like that kind of reverse order there. So -3, if you go over here, it's just barely negative. Then -2, it's -1/2. At -1, it's also -1. And then you go to -1/2, then what happens is you jump all the way down here. And as the x is slightly negative, the further down you go. We're good? So this we call sometimes we put a little dashed line coming down like this. A vertical dashed line. It has a little special name. It's called a vertical asymptote. Took me a while to figure out how to say that. Okay. Vertical asymptotes are points along the graph where there's a break in the graph, and the graph goes closer and closer and closer and closer to it, but never touches. Same thing on this side here. The red line is getting closer and closer and closer to the y-axis, and forever, but never touches it. Okay, we good there? All right. Also has another asymptote. This one's called a horizontal asymptote. Now these rational equations, most of the time they have a horizontal asymptote. Now this one's, again, it's a horizontal line. So as the x values become more and more negative, the graph itself tends to sort of get closer and closer to a certain line. As the x values get more and more positive, again, it sort of just kind of curves to a certain point. And this is kind of funny. This guy will go on forever, 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 getting bigger. Bigger x's, and this line will forever, forever get smaller and smaller, right? Because let's say if you put a 5 in here, this is 1/5, right? If you put a 10 in here, now it becomes 1/10. If you put 1,000 in here, it becomes 1/1000. So this red line is getting closer to the x-axis forever, but never touches it. Okay, so that's sort of the general idea you should sort of have on these. They kind of go like this. They kind of curve to a vertical asymptote, curve from a vertical asymptote, and they somehow get close to a horizontal asymptote on each side. So this is what we're going to do. For number 5, let's graph y is equal to 2 over x. And of course, we have to make a little table. Based upon a table, we'll put them together. And then we just want to get a general feel for how does this look. That's all. All right, first things first. Here's my table, -4 plugged in. And if I put a -4 in here, simplifying out, that would give you a -1/2. Plug in a -2, and now I'll let you do that as well. -3. Then plug in a -2, then plug in a -1, maybe go all the way up to +4, and just see what kind of numbers we get. All right, looks like most people are done or almost done with the graph here, so let's check our numbers here. -2/3. How about a -1, a -2, and this guy is undefined, is that right? Plug in a 1 becomes a 2, plug in a 2 becomes a 1, plug in a 3 becomes a +2/3. And I didn't have time, I didn't have room for the 4 here. What did you guys get when you plugged in the 4? 1/2. Okay. So first things first, this little undefined term, our restriction that we talked about in 6.1, we're going to put a dashed line coming straight down like this. Our vertical asymptote is set. And then let's plot these points, and then let's see if we can sort of combine them together. So at -4, 1, 2, 3, 4, we get a dot of -1/2. At -3, we get a dot of -2/3. The -2/3 is more than halfway down to -1, so about right there. At -2, we get a -1. At -1, we get a -2. So you see the little starting of that curve pattern. Okay, real quick here.
How do you get the asymptote thing?
This one right here. Asymptote came from when the number is undefined.
You
Or-
automatically put that in first?
Yeah,
Well, how come?
Because then I know exactly where is going to be a break in my graph. Because graphs will never, ever, ever, ever touch a vertical line or the vertical asymptote. So you have to sort of see where the curve is. The curve is going to curve right here, and then you have to make more and more of a curve so it doesn't touch this blue line.
And the 0 undefined is straight on the y-axis.
Mm-hmm. Okay, let's go some more here. No, let's actually graph this line here. So, see if you guys agree here. Kind of goes like this, starts curving. Then you want to curve it out so it doesn't touch the dashed blue line. Gets closer and closer, but there we are. All right, on the other side, 1 goes to 2, 2 goes to 1, and 3 goes to 2/3. And if you want to do -4, it'd be a -1/2.
Will the asymptote line ever change around? Will it go horizontal and vertical?
This is called the vertical asymptote. That one can move left or right. It can shift.
Oh.
That's probably more of a Math 63 topic, because I don't think it
Oh, okay,
shifts.
so it'd always just be.
And the way it shifts is you just put x like +3 or x -3 on the bottom. And because of that, then you got shifting, because now you're saying, hey, x can't be -3. That's where the shift comes in. All right, curving this line, again, any which way you can. It's going to start up high real quick here. It's going to quickly go down, and then it's going to start slowly to curve. And it's never going to, there's never a time where this will give you a 0. It'll just sort of get closer and closer. So there is a horizontal asymptote. Those are not that important as far as making the graph. Okay, we good there? One more, very similar to this here. Number 6, all it is, I switched it to a negative. So it's -2/x. So how does that play into?
It was on the side.
So -4 plugged in, -3, -2, -1, 0, 1, 2, 3, and 4. So I'll let you guys try it yourself.
Just like when we graph with the quadrant.
All right, here, let's see, plugging in a -4. I'm going to give you answers here, see if we agree before we start the graphing here. So the 0 made it undefined, is that right? There's a problem, there's our restriction. But I got a 1/2, positive 1/2. Cool, all right, how about a positive 2/3? 1 and 2. On the other side, -2, -1, -2/3, and a -1/2. And really, it's the exact opposite of number 5 as far as answers go for the y variable. Okay, let's go for it again. X equals 0. That vertical line is going straight down on the y-axis. As we plot these at -4, now we're going to actually go up a half. -3, we're going to go up 2/3 of the way to 1. At -2, we're going to go all the way up to 1. At -1, we're going to actually jump all the way to +2. So then you kind of sort of see where that curve is heading. Curve is heading that way, therefore it's almost like this. It's down low over here, and then it starts curving, and like that. Shouldn't really go back on itself. That's my little mistake in drawing here. Shouldn't sort of go back out anymore. Should get closer and closer to the blue hash line. Okay, on the other side, 1 goes to -2. 2 goes to -1, then -2/3, -1/2, and then you can kind of see what's happening to the curve here. Starts out then very, very low, and then never comes up to the x-axis. And always, of course, the question is, Mr. H, can it actually come up to the x-axis? Yes, those do that, just not in Math 61. All right, good there. That was 6.5. Word problems and graphing. Let's jump to 6.6. And we start something called the complex fractions here. So, wow. As if fractions are not bad enough, now we have something called complex fractions. So, first of all, what does complex fractions mean? That means we have fractions within a fraction. So this big bar line right here, for example number 1, this big bar line, that's the fraction of 1/2 and 2/3. So the big bar line is, so 1/2 is dividing 2/3. Alright, how do we do that? Again, there's 4 problems here, but as a quick example here, there's 2 different methods to do it. Method number 1 is what you do is you find a common denominator. So the 1/2, 2 is the denominator, 2/3, 3 is the denominator. Common denominator of 2 and 3 is 6. And what we're going to do is we're going to multiply both top and bottom by 6. But real quick here, what are we actually multiplying by? We're multiplying by 6 over 6, right? What's 6 divided by 6? Yeah, we're really technically multiplying by 1, and that's what keeps it all the same. And so we're allowed to multiply both top and bottom fractions because we're really multiplying by 1. It doesn't change the problem. Cool. So 1/2 of 6 is 3, 2/3 of 6 is 4, and done. That's one way to solve it. And that's the one we're going to practice here. The second method is what you do is you really think about this here. This means quotient, right? This means divide. So if it's 1/2 divided by 2/3, or maybe you even write it like this because this is the way I think you guys remember it. If you say 1/2, quotient of 1/2 and 2/3, this also means 1/2 is being divided by 2/3. Everybody agreed there? But then we have this little rule. Instead of dividing fractions, all we do is we multiply them. So we change the division to multiplication. We switch or take a reciprocal of our second fraction, and then we multiply straight across, and we're done. This one's probably the easier one, especially if you just sort of think of numbers only. But again, we're going to think about variables, and that's what's going to make it a little more complicated. Okay, so let's jump into it here. Let's see. Number 1 is a pre-algebra problem, just to get us used to this stuff here. So we're gonna practice with method 1 here. So 1/5 is being divided by 2/5. What is the answer? Well, let's see. First of all, what we're gonna do is we're going to multiply by the common denominator. What is the common denominator? 5. So let's multiply the top by 5, the bottom by 5. Okay, on top, really the 5's cancel. So really the whole entire top really just becomes a 1. On the bottom? Yep, the 5's cancel as well. And since everything cancels but the 2, we got ourselves 1/2. We're done. Of
what
course.
if you, well, you kind of did the same thing. Cross multiply? Like put 1 over 5 times 5 over 2, and then cross multiply, and that leaves you with 1/2. Did you get what I said?
All right, let's go on to this one. All right, let's look at this one here again. Practicing method number 1, just so we get used to it here. What's my common denominator? Y to the fourth, fifth, which one?
Fifth.
We're gonna go with fifth one, yep. Always the biggest exponent. Okay, on top then, the 5.
Try it with both methods.
Absolutely. Yeah, we can try both methods here. Y to the 5th cancels. How about y to the, ooh, this one's gonna have an extra y on top right here, right? Everybody okay with that one? So now let's see. On top, I'm left with a 5x to the 5th. On the bottom, I'm left with a 10x squared y. Ooh, got some more reducing here. What should I reduce? 5 and the 10. How about a 1 and a 2? Anything else? The x's. I got x to the 5th on top, x squared on the bottom. That means I'm going to have an extra x to the 3rd on top. So how about x to the 3rd over 2y is good. All right. Kelly, you want to see it the other way? Let's go for it. The other way would be 5x to the 5th over 5y multiplied by y to the 4th 10x squared. All right, looking at this here again. That's going to become, and that's going to become a 1. That becomes a 2. And how about y to the 5th, y to the 4th? So an extra y in the bottom here. That's all gone. So just a 1. Ooh, almost forgot. X to the 5th, x to the 2nd. That's gone, and that's gone. That leaves us with x cubed on top. Good there? Cool, I think we're done. 1, x cubed 1 makes x cubed. 2 times y is 2y. All right, number 3. Dealing with binomials now. Got pluses and minuses now in here. Okay, and this one, notice, if you sort of start thinking about it, notice method number 2 is not really going to work in this scenario. You can't put that over that, and because that's not going to work. Method number 1 is the one that's going to have to be the one that we work with. So common denominator is y is good. Let's multiply by y. In this case, we have to distribute the y. So distributing the y to the x, there's no fraction here to cancel or anything. So it's just x times y or xy. As the y distributes to the second term here, the y's cancel. Yeah, the y's are gone, so we're left with just a minus 1. All right, on the bottom.
X, Y plus 2.
That'd be good by me, yep. X times y is xy, and then as the y distributes, the y's cancel, but leaves us with a plus 2. Can I factor? Can I reduce?
Yes, the X and the Y.
Okay, I disagree.
This one's a negative one.
Yeah, because on top, do you have a single term on top?
No.
Yeah, I have a single term of xy minus 1, right? This minus sign is keeping the xy and the 1 together as one single term. If you were to put parentheses around something here, let's do it that way maybe. If you're going to put parentheses here, where would the parentheses go?
And then X.
This guy's holding it together though, right? Careful here, that's holding it together.
So on the 1, the negative 1.
So that's one piece, right?
Well, you can't break it up. It would be a different.
Because one's a negative, one's positive, right?
Yeah, but you can't break this up into
Yeah, you
something
can't, or it'll
smaller.
change the answer.
And so this is a certain term. So are those terms exactly the same to cancel?
No.
No, it's the little minus and plus keeping it together. It's keeping the 1 and the x squared. Plus sign is keeping the 2 and the x, I'm sorry, xy. plus sign is keeping the 2 and the xy together. So you cannot cancel things that are different. Okay, we're good there? Next, number 4. Notice I cannot do this by method number 2 again. So method number 1 wins. Alright, common denominator. X squared is perfect, yep. Let's multiply both top and bottom by x squared. Let you guys do that. Let's see what we come up with.
On the bottom one, that x, would it also get canceled out, or?
The question is on the bottom, probably right here you're
Yes.
asking, right? So the question is, does this x get canceled out? Yes, one of these x's will cancel one of these x's. But you still have an extra x that you're multiplying with. Alright, so let me try this as well. Multiplying through the x squared times 1 is x squared. Multiplying to the second term in the binomial, the x squareds cancel completely, so just left with plus 3. On the bottom, multiplying the x squared all the way across to the 1 over there, so you get x squared. Multiplying the x squared to the middle, here's the toughy one here. One of the x's will cancel. We still have another one that's still multiplying, so how about a 2x? Good there?
No, I got 2x3.
Okay, so let's take a look at it here. So off to the side here, let's see this multiplication take place here. So it's 2 over x is being multiplied by x squared. We change this into a fraction. And then what happens here, this x here is going to cancel with this, leaving an extra x on top. That's where your 2x comes from. And x squared into that, x squareds cancel completely. How about a minus 5? Alright, the only thing to do from here, since I see x squareds, I see x's. Question is, can I factor? Alright, sometimes you will, sometimes you won't. In this case, can I factor? No. So then that stays as the final answer. If you can factor, then yes, then you have to keep on going to factor. So if this was an x,
Break down like the bottom part.
This one?
Trinomial thing.
yeah. So that's the question. Does this factor? Does x squared plus 3 factor? It doesn't, because 3 is not a perfect square. On the bottom, can I get two numbers and multiply to 5, add to negative 2? I'm sorry, negative 5, but add to positive 2. Not possible as far as integers are concerned. Maybe possible with square roots, but we haven't got there. Alright, good there? And that concludes the lecture for 6.6.